In this video, we're going to explore molecular orbitals and get into a little bit of molecular orbital theory. And we're going to do this using hydrogen. Now, why do we want to think about molecular orbital theory? Well, to understand the structure and reactivity of molecules, we have to think about how their orbitals interact. And we can certainly do this, and physical chemists do this all the time, at a very mathematical level, thinking about the Schrodinger equation and the wave functions of atoms and of orbitals. However, we can do this in a very non-mathematical way as well. That kind of simplifies things, and that's exactly what we're going to attempt to do, is simplify um, atomic and molecular orbitals to try to understand what's going on and to try to predict reactivity. So let's look at hydrogen. We've seen we've seen this kind of figure before, where if you take hydrogen and you plot the atomic distance between the two hydrogens relative to energy, you get this curve that looks something like this, where um, the blue dotted line represents the energy of two hydrogens that are separated completely, right? So we start off at the far right end of our figure, of our table here, and what's happening? Well, now as we move to the left, the distance between the hydrogen atoms is decreasing. So we start off at some point here. We now move to a dot here. Hopefully you can see that little red dot that I just placed. What's happening? Well, now the hydrogens are starting to form a bond. So notice the energy is decreasing. Energy is being released. Why? Because at this stage, the electrons from one of the atoms starts to interact with the nucleus of the other atom. So at this particular distance, now we have what's called electron nucleus interactions. Again, electrons of one atom are beginning to be attracted to the protons in the nucleus of the other atom. And energy continues to be released until we reach this minimization. Now why? Well, at this particular distance, now we've created this is what we call the hydrogen-hydrogen bond distance, right? And that bond distance is 0.74 angstroms. And this is the distance in which the electrons of one atom interacting with the protons in the nucleus of the other atom are ideal relative to the protons of one atom repelling the protons of the other atom, right? Because you have two charges that are kind of competing against one another. Now, as you move closer, as you push those atoms closer together, you see a sharp increase in energy. And the reason for this, and I'm depicting it as two hydrogens that are squished together, the reason for this has to do with proton repulsions, sometimes referred to as nuclear repulsions, nucleus-nucleus interactions that are repelling one another, right? So this is this is a diagram that really gets to understanding what's happening at the molecular level of two hydrogens. But what's happening is you're combining in essence, you're starting with two atoms that have orbitals, and you end up with a molecule that has orbitals, right? So two atoms forming a molecule. In essence, we can say that we're combining two 1s atomic orbitals, which have a wave function to them, psi. And when we do that, we produce two new molecular orbitals, which we are going to call phi, right? So psi we denote as atomic orbitals. Molecular orbitals we're going to denote as phi. Terminology, don't worry about the terminology too much. I mean, just, you're going to see some textbooks use psi all the time. Sometimes I'll use psi all the time. It's an arbitrary representation um, of orbitals, be they atomic orbitals or molecular orbitals. So the important feature is how this is taking place. All right, so we start off with an atomic orbital of HA. And that atomic orbital we're going to note as psi of HA. We can combine that, add it with the atomic orbital of HB, which we're going to describe as the wave function of HB. And when we add the two wave functions together, we get a new wave function, which we call phi B. The B stands for bonding. So phi bonding. So this is a new molecular orbital. It is a bonding molecular orbital between HA and HB. Now, an important aspect of molecular orbital theory is that when you combine two orbitals, be they atomic or molecular, when you combine two orbitals, you must produce two new orbitals. So notice what I said up there. So in this process, they're coming together, they're bonding together, but I've only produced one orbital, one new molecular orbital. There has to be another one. What is that other one? Well, the other one is when we take HA, the wave function of HA, because remember these are wave functions, and we subtract the wave function of HB. The result is that you get an antibonding orbital, right? And we denote it like this, where now HA, sorry, that structure on the left says HB, should be HA. So HA is interacting with the orbital of HB that is out of phase with HA, right? And so I'm denoting it green. And these two orbitals cannot interact with one another, and therefore there's a nodal plane, a node between the two orbitals. So there is a non-interaction. Actually, it's a repulsive interaction between the two. And we call this phi A, or phi antibonding. A simply stands for antibonding. So phi bonding and phi antibonding. Now, when we think about the energy of the orbitals, we start off with two atomic orbitals, HA and HB. And as we saw in the diagram on the previous slide, energy is released, so energy is lowered, and it produces a bond between HA and HB. And this is represented by that phi bonding orbital, that new molecular orbital. It's lower in energy. Well, what about phi A, phi antibonding? Well, the net energy is maintained in a particular system, and therefore the phi antibonding is at a higher energy level. And in general, whenever you have a node, it's going to have a higher energy level. And so we get an energy diagram. Remember, this is an energy diagram that shows that when we mix two atomic orbitals of hydrogen, they produce a molecular orbital that's lower in energy, more stable, and they produce another orbital that's higher in energy, which is less stable, right? So here we're now developing why we get a molecular orbital. It deals with stability. And that's the important feature of this. Okay, so some points to note. When electrons are in a bonding orbital, they hold the nuclei, the two nuclei, together. When electrons are in an antibonding orbital, they repel, right? This is referred to as dissociation. They repel or dissociate the nuclei. In our example of hydrogen, all we have is a bonding orbital and an antibonding orbital. Notice we haven't added electrons yet. So if electrons add to the bonding orbital, they're going to hold the nucleus together. If the electrons are added to the antibonding orbital, they're going to repel the nuclei. So the nuclei actually split apart, and you can't really form a molecule between those two atoms. There is another type of orbital, and that's called a non-bonding orbital. And we'll look at examples of this in the future. But whenever there are electrons in non-bonding orbitals, they really have no effect either way. They don't hold the nucleus together, the nuclei together. They don't repel the nuclei. They're simply there. The other thing that's important to understand is that when two orbitals come together, they always produce two new orbitals. When three orbitals are combined, they always produce three new orbitals. When four orbitals are combined, they produce four new orbitals, and so on and so forth. And so this is an important concept to understand, okay? Okay, so let's add electrons. And when we add electrons to a molecular orbital diagram, they follow the same rules as those of filling atomic orbitals, right? So at the very beginning of the chapter, there's a nice little review of how electrons go into atomic orbitals, right? And this deals with the Aufbau principle, the Pauli exclusion principle, and Hund's rule. So these rules still apply to molecular orbital diagrams. Now, let's construct our diagram and see what happens. Again, we start off with two atomic orbitals, or the wave function of two atomic orbitals, HA and HB. We produce two new orbitals, molecular orbitals, Phi bonding and Phi antibonding. So the Phi bonding is the addition of HA and HB, and the Phi antibonding is the subtraction of HA and HB. When we start, each hydrogen has has one electron, right? So the electron of HA is here, and the electron of HB is here. Now, I arbitrarily drew the arrows pointing up. Oftentimes you'll see one arrow up and one arrow down, and the reason is because in order for them to populate an orbital, they have to have different spins. So sometimes you'll see HB having the opposite spin, such that when they come together, now what happens? Well, again, now we're looking at molecular orbitals, Phi bonding, Phi antibonding. Well, the Phi bonding is a lower energy, and so I'm going to add an electron to that Phi bonding, and since it's a bonding orbital, it can take on two electrons. So I take one electron from HA, I take the other electron, which has the opposite spin, from HB, and both electrons go into that new bonding molecular orbital. Notice no electrons, because we have none left, go into the antibonding orbital. And therefore, when the two hydrogen atoms come together, they release energy to give me a molecule that is hydrogen, H2. And the difference between the energy of the atomic orbitals and the new energy of my bonding orbital is referred to as the stabilization energy. And we'll see kind of what that entails in just a little bit, right? But it's the stabilization energy. Now, one thing to understand is that spatial orientation of orbitals is very important, right? We cannot simply take two orbitals and combine them together in any particular spatial orientation. And let me show you what I mean by that. If I take a p orbital and I combine it with an s orbital, right? So a p orbital, an s orbital is symmetrical. A p orbital has two distinct signs to it, right? And I'm denoting those two distinct signs by color change. So one lobe is blue, the other lobe is green. Now, we need to understand that green can't interact with blue, okay? So when an s orbital approaches a p orbital, I can have really two types of possible interactions. Obviously, the s orbital can't approach the green lobe, but it can approach the blue lobe. And when this occurs, there is an interaction between the two, and they can overlap and form a new molecular orbital. And this is what we call bonding. Now, there is another possible orientation, and that is if the s orbital approaches the side of the p orbital. So here's my p orbital, there's my s orbital, and it's approaching the side of the p orbital. Now what happens? Well, notice it can interact with the blue lobe, right? So I can get an interaction there, and that would be a bonding interaction. But also notice it's also in very close proximity to the green lobe. That is an antibonding interaction. So it cannot bond there. And if we take the net effect of this, each bonding and antibonding interaction cancel one another out. This is referred to as orthogonal orbitals, right? When two atoms do not symmetrically, spatially interact with one another, it's called an orthogonal orbital. Now this can be a little bit misleading because you think, oh, it's an orbital. It's not an orbital. And the reason for that is because there is no mixing that occurs. So this doesn't exist whatsoever. So when you're mixing, you have to think about the shapes of the orbitals, which is why it's important to review the shapes of the s orbital and the p orbitals. Mainly those two, because those are the two types of orbitals that we're going to be looking at in organic chemistry, along with hybridized orbitals, which we'll get to in Chapter 2. Now, we can also mix a p orbital with another p orbital, right? And when we do so, we can have a very good, strong interaction between the two p orbitals in which the signs are aligned with one another, right? So the blue and the blue can come together, and the green can come together. And so this is a good, strong bonding orbital, and we actually call this a pi bond. That's exactly how two p orbitals come together. Conversely, you can have a p orbital that is perpendicular to another p orbital. Now when this occurs, it's very similar to when an s orbital interacts with the p orbital. Notice I have a green lobe and I can get bonding to occur with the other green lobe, but I also get antibonding of the blue lobe. And therefore, since I have both interactions, this is also an example of orthogonal orbitals, right? These are orthogonal orbitals. And so we have to understand, how spatially two atomic or molecular orbitals kind of come together, and that there are limitations to the orientation of those orbitals. Now, how do you figure this all out? Well, there are some guidelines that if you follow, it starts to make it a little bit easier in terms of predicting molecular orbitals from atomic orbitals, right? The first one is, again, the number of orbitals produced equals the number of orbitals you are combining, right? So if I take two orbitals, I combine them, I always get two new orbitals. And one can be bonding and one can be antibonding. If I take three orbitals, I always get three new molecular orbitals. The second guideline is always combine orbitals in a symmetrical way, such that their signs line up, okay? That they are in phase with one another. Also, understand that orbitals that aren't shaped the same have weaker interactions. So two s orbitals, strong interaction. An s and a p orbital, not so strong interaction. Two p orbitals, strong interaction, right? And so you'll kind of get the feel of this as we go along. The third guideline is that stronger interactions, well, and I kind of already said this, stronger interactions occur with two orbitals that have similar energy and size. So I already said S interacts with S, P interacts with P. But also it has to do with the principal quantum number, right? And we're going to see that, when you have an atom that has, let's say, a 2s orbital, interacting with an atom that has maybe a 5 s orbital, they don't combine as well as two atoms that have the same principal quantum number. And so that has to do with energy and size. The fourth guideline is that understand that bonding interactions lead to a stabilization. So this means a lower energy, right? It's more stable, energy is released, and that antibonding orbitals lead to destabilization. So when we form bonding orbitals, we stabilize. When we form antibonding orbitals, we destabilize. Or I should say, when we populate bonding orbitals, we stabilize. When we populate antibonding orbitals, we destabilize. Populate by electrons. The fifth is that when two orbitals interact, the only options for mixing them are in phase or out of phase. So you can add them or you can subtract them, just like we saw with hydrogen. And the last option is, or guideline, is that energy increases as the number of nodes increase. Notice that my bonding molecular orbital had 0 nodes. My antibonding molecular orbital had 1 node. And the antibonding orbital was higher in energy. So the more nodes you have, the higher the energy of that orbital is going to be. I hope this helps you out, and we're going to explore molecular orbitals of molecules in the next few weeks.